Okay guys, let's start lesson. So can I quickly just go through the last practical, the last part again? This one I went through with you already, right? Didn't. The last practical that I returned you, the resistance of a thermistor. There's one part at the end that says assuming a potential difference depends on the temperature. Okay, that part. Okay, never mind. Wait, I explain it.
I thought you went through last one.
I went through it, yeah. Okay, so I think my other two classes I haven't gone through it. Okay, no problem. Let's do a tutorial for its superposition. So you have a try. Is it doable? Or is it that difficult?
What's wrong?
No big tutorial. Look at it. No more Ethan. Guys, take a look at question 1. So most of you have made this mistake. Now I give you a chance to rectify it. The question tells you in question 1, right, that the wave is a continuous wave. Which means, right, even at t equals to 0, right, the wave has already met the wall. So there's already reflected waves already. Okay, that means it exists before time t equals to 0. It's just at that point in time, this is what the incident wave looks like. There already is reflected wave. Okay, so go edit your answer. Okay, go think about it. Okay, so we're treating, okay, remember when a wave hits a wall, right, is either you treat the end as a fixed end, okay, and then the standing wave can form will be a node, or you treat it as an open end. Open end means it will be an antinode, right? So in this case, right, they're saying that when microwave hit the wall, right, it will be like a fixed end, because they say there's a 180-degree phase change. Remember I showed you the case of the rope wave. When you hold the rope wave at the end, right, you will, when the pulse comes in, a crest will become a trough, so there'll be a flip of the wave, right? Whereas I showed you a case where the end is free to move. When you send the crest, it bounces back as a crest. Remember that video? Yeah, so in this case, right, they're saying that the reflected wave got 180-degree phase change. Okay, so that's for a fixed end. Okay, come. So what do you think the outgoing wave will look like? Oh, by the way, did anyone do practical last week? Didn't? Alright, last week no one. No one missed the practical last week, right? Right, so this is the incoming wave. How does the outgoing wave look like? You want to sketch for me, Abby? The mic? Let's try that. Okay, so now we all know a reflected wave. So once Abby gets the correct reflected wave, we know how to do it already. How to do it? Why? Yes, okay, good. Go sketch it. Start together. And then draw the arrow direction of the wave down for position.
Oh, I got pranked. I thought
No, that's this is for the orange.
that's not quite
So draw one more axis. Yeah, it's flat, right? Because now they just left cancel one another.
wow. You spent quite a bit more already.
No, there's nothing. Because standing wave. I mean, it's a good part. The resultant wave doesn't confirm yet, right? So you just draw a straight line. Draw a straight line, then you just say no resultant. Yeah, that's Amanda, you just dirty the classroom with some. Okay, great. Okay, so guys, take a look. Abi did sketch the correct graph. He got the reflected wave, but the reflected wave has 180-degree phase change, so we'll flip. So basically, your wave, right, will flip in the y-axis, along the y-axis, right? So that's to do the reflection. Then it will flip down if there's phase change, that means it will reflect in the x-axis, or it will not reflect in the x-axis if there's no phase change. So it depends on the boundary that you hit. So in this case, the question is telling us is hitting a boundary that there will be a 180-degree phase change, so it will flip in the x-axis as well. So actually, if you're not very sure how to visualize this, right, there's a trick. Okay, the trick is, you imagine that the wave continues forward into the mirror. Okay, whatever's reflecting. Right? Then the y-axis means this whole wave will flip this way. So you take this and you turn it this way like that. Right? So actually it should be on top and below. But then because of the phase change, right, then it gets flipped this way. Right? So you end up with cancellation throughout, and you get no resultant wave for this. Okay. So this is for t equals to 0, right? Let's do t equals to quarter wavelength.
So I got break, I got straight up break.
Okay, no matter, since you got prank, right? Now you will have a chance to redeem yourself. Okay, if this wave is look like this, right? What will the wave look like the quarter cycle later for the incoming wave?
But incoming is
Yeah.
it will stop at
Stop at where? Stop here?
1/4 yeah.
Okay. So it will look like this, right?
Yeah.
This is the incoming wave. So then what's the outgoing wave now? Can you visualize? Will it be opposite like this, or will it not be? We'll figure out. See, how do you get this, Johnny? How do you get this? But how do you get okay, it's reflected twice, right? It goes this way and tilts it. So you must reflect the wave that goes through. So you draw the wave that goes through first. So now this wave gets reflected this way, right? Then the phase changes. Right, so you don't just try to assume, you try to think of a way that you can really think of one flip and the other flip. Otherwise you will get it wrong if you just try to guess. Yeah, you usually just take the y-axis first, along the y-axis, because always get reflected. Then whether the phase change or not is whether it fits in the x-axis or not. Yes, good. Okay, then let's get the resultant now. Yeah, can use blue one for the axis. Yeah, so actually this kind of thing, right, you really need to very step by step do it. Okay, how does this relate to the amplitude here? So let's say the amplitude here is A. How does this amplitude relate to it? Go draw a label there as this. Yeah, okay, can. So this is the case where you get double the amplitude because the waves add up, right? So actually just now she said, oh, you look at phase change, so she flipped the wave. So that's actually just a guess from understanding that the wave flips. But you must know that the wave first reflects. Right? So you must sketch the reflected wave in your mind. So if the wave goes this way, right, it means it's continuing like this. Which means that the reflected wave will be up, then down. Then there's the phase change. So you do it step by step. A flip in the y-axis first. No matter what, all reflected waves get a flip in the y-axis. Then, if there's phase change, then you flip in the x-axis. If there is no phase change, then you don't flip in the x-axis. Okay? So what you end up with is this. Okay, so this is T for T1 quarter. Orange is for this. Okay, JJ, that'll be what you can do, right? So one more half quarter cycle later, you get T over 2. What does the incoming wave look like? Just tell me where will it start? Where will it start? Here? Where? Where's the quarter? Here? In between? Okay, then. Alright. Okay, so this is where what the incoming wave will look like. It's progressing by quarter wavelength, so you can see quarter wavelength. These are the quarters, right? Yeah. Okay, so the outgoing wave now, we will continue again. You use the technique that it comes out this way. So you will flip in the the y-axis, then you flip up. So now we get back a similar pattern to t equal to 0, but now it's in the opposite direction. So you end up with resultant is 0 again. Right, can you see that? Okay, so if you can't see if this continues, and then you flip it and then flip it. Okay, last one, you should expect that you will get this one again. Because one more quarter cycle later, they should add up, right? So now, you hit the wall like this at equilibrium. And then it continues this way. Flip, so it reinforces. Okay. So your resultant is same as what Jolene dropped, but now it's up instead of down. Up. And design this 2a. Okay, so now we can see the pattern of how they form, right? Of the resultant waveform. Can you tell that it's a standing wave? If it's a standing wave, right? Where's the nodes and antinodes? At the wall? Is this a node or antinode? No. Here, antinode. Here, node, antinode, node. So you can see the nodes never oscillate. But the antinode down will go back to equilibrium, then will go up. Then later on it will go back to equilibrium, then will go down, then go back to equilibrium, will go up. Yeah, so the rule that we'll end up with, right, is fixed n. If you have a fixed n, this one is the 180-degree phase change. And then this one will end up as a node at the end. Then the open end, or the not fixed end, right? Open end. You have no phase change, that means you don't flip it in the x-axis, and then it will be an antinode. Okay, actually, you think about it, it makes sense. If you fix n, right, you can't move. So if you can't move, you have to be the node. And if you open n, you get to move. So you move from maximum to minimum. So you'll be antinode. Make sense? Yeah, I showed you on the video, remember, the crest will reflect backwards, the crest. So it's just a reflection of, right? But you saw the video, right? So you can visualize it actually happening, right? Good enough, lah. Good enough. Okay, my later I'll have one more example where you can help you visualize, okay? Not to worry. Okay, thanks for the help. Everybody will help. What's this doing here? It's all like okay, let's look at question 2. So standing wave is produced again. And then we have a few points that we want to talk about. This is A, this is B, this is C, this is D, and this is E. Right? So which are the nodes?
A and B.
A, B are the nodes. Which are the antinodes?
C and E.
C, E are antinodes. So B is neither a node nor an antinode. A is just another point that's oscillating. So the question says describe. Okay, how I describe in this question? Brandon, how do you describe? I know Brandon's mind. Okay, yeah, how will you describe? Describe the A and B.
A and B.
Yeah, the question says describe, right?
I say that they are not oscillating.
They are not oscillating. You said they?
Oh, A and B.
Ah, okay. So and this kind of question, right, the phrasing is important.
No, because you said A and B, what I just said they.
I mean, referring to the question. So what will you say?
Okay, A and B are not oscillating.
Okay, but A and B are not particles. A and B are points on a line. So what you want to say is particles Because A and B is a position, right? But actually the position does not oscillate. It is the particle that happens to be at that position that oscillates. And if it's electromagnetic field, it will be the electric field at that position that oscillates. Right? So particles at A and B do not oscillate, but remain at equilibrium, or it remains stationary at equilibrium. Good enough. Okay, something like this. Okay, other method, how about particles at the antinodes? How will you describe them then, given that this is how we describe A and B?
Particles at C and D.
Good. Particles at C and D.
Oscillate at different
Maximum? Sorry? Yes, amplitude.
So syntax displacement wrong.
Cannot.
Wrong.
Do you know why maximum displacement cannot? What's the definition of amplitude? Two topics ago.
Displacement from starting point.
Correct. Amplitude is maximum displacement already. Right? Each of the particles in the standing wave have their own separate amplitude. So if I just say that they are oscillating with maximum displacement, I'm just saying that they are oscillating with their own maximum amplitude, which is not wrong, but it's not complete. It is not only that they oscillate with maximum displacement, they oscillate with the most maximum displacement, right? So that's why I must say maximum amplitude. Right? So it's not maximum displacement, but maximum amplitude. Because amplitude is already maximum displacement. So basically what I'm saying is that all the particles here, they have their own amplitude. But at C and E, right, because they are sorry, not D, C and E, because they are at antinodes, they will oscillate the maximum possible amplitude. So they have the maximum displacement. Okay, Alan? So cannot just say maximum displacement, must say maximum amplitude. So how definition? Amplitude must know how to say, must know how to define, okay? It's maximum displacement. So it's maximum amplitude. Okay, can you see how they go to D? How we describe D? Start with particles at D. Okay, oscillate. Maybe compare with C and E. No, not displacement. Amplitude, right? Oscillate with a smaller amplitude. Once you're comparing amplitude, right? Compared to C and E.
Can we talk about the phase difference?
Yes, then now we talk about phase difference. Because now we're only talking about the oscillation, then we talk about phase difference, right? So, who and who are in phase?
C and D.
C and D are in the same segment, right? So we will mention that C and D are in same segment. Therefore, in phase. C and D and E are in not different. Must be specific. Okay, they're anti-phase, but how do their segments compare? Correct, this word adjacent. Because different segments, right, can be these two segments. These two segments are different segments, but they are in phase. Right, so they are in adjacent segments. So therefore, anti-phase. Or out of phase. Okay, so this is the kind of language we need to use. So be specific. You don't say points oscillate. Points don't oscillate. It is the particles that point that oscillate. Right? Then your description should include basically a coverage of position, velocity, and acceleration. That's what I mean when I say describe. Like instead of describing Amanda is a girl, blah blah blah. Everything in physics is, Amanda is a point particle with particular position, velocity, and acceleration. So currently she has position behind alloy, 0 velocity, 0 acceleration. That's what we mean in physics by describe. Okay, we don't really care about the other appearance. Everything is point object in vacuum. Right, so position, velocity, and acceleration are important. So if you look at this statement, I can tell that, see, I can tell that position, that means the position is changing with oscillate. I know oscillate could be some kind of SHM or may not be, but at least I know that there's velocity and acceleration because there's oscillation. And I can tell that the maximum possible displacement, another way of indicating position is through amplitude. It will have highest amplitude. Right, so I'm actually taking care of S, B, and A.
For particles that we oscillate with small amplitude, can you just oscillate at a point, like oscillate less than the maximum amplitude?
Yeah, but less is vague. What's less? So in physics, you want to get good answers, right? You use the terms for each topic. So in particles, right, you talk about the particle's displacement, velocity, and acceleration. When you talk about waves, right, you talk about the particle's amplitude, displacement. You can also talk about its period of oscillation, frequency of oscillation. Then we talk about a wave, you can talk about the wavelength, the period of the wave, and the frequency of the wave and the speed of the wave. So you think about what physics quantities describe the thing you are talking about. So in this case, it's particles oscillating, right? So you don't say it oscillates smaller. What's smaller? Your amplitude smaller. Okay? Yeah. Yeah, use the think of the terminology. So basically put a little bit more thought as you're answering these kind of qualitative questions which you are generally not so good at. In calculation questions you're usually okay. So this is how you improve your answer for qualitative questions. Think of the physics quantities to talk about. Okay, wavelength is easy, right? John, what's the wavelength? If this is L,
Half L.
how do you know?
Because L is for 2 cycles.
How do you know? Right, these are nodes, right? So how do you compare?
Alright.
Compare nodes to the cycle. This is how many cycles? Then we use that. So we'll say D node to node. So I know you know that it's L over 2, right? The wavelength is L over 2, but we want to quantify it more specifically. We'll say that the distance of node to node is wavelength over 2. So L is 4 node to node distances. So it's 4 times lambda over 2, which gives me lambda over 2. 2 lambda, sorry. So basically, I'm trying to think of how to explain my working a little bit more. So you just tell someone, it looks like what? Hey, I look like a C4 cycle like that one. Right? So you can explain through the node to node distance. Right? So therefore L equal wavelength over 2.
You have to show this calculation. You have to show this calculation.
Yeah, if you are going to show calculation, this is what you should show. You compare to the node to node distance. Because this is standing wave, the characteristic of standing wave is where the node and the node are. So it's good to compare to the node to node distance. Okay? Okay, question 3. If you didn't get the answer C, then something is wrong. Okay? But there's a bit of new information that you have learned today. It is from question 1. It is from whether it's a fixed end or an open end. Okay, I want you to take note, right, that when the wave hits the wall, right, it's not at maximum at this point in time. Okay, it haven't reached maximum yet. Or the maximum has already gone through the wall, sorry, it's already past maximum. Okay, so the hint is, in question 1, right, we learned that fixed ends, right, will give us nodes. Open ends will give us empty nodes. Okay, so if you got the answer wrong, you only got the answer wrong. So now you can think about it. Okay, if fixed ends give us nodes and open end gives us empty nodes, is this an open or fixed closed or fixed end? Okay, if you don't know, think back to your childhood days or your current days when you go swimming. Okay, you have looked at the wall before. I mean, it's something. Yeah, have looked at the wall before? How does the Hadouken come back? But when we hit the wall of the swimming pool, yeah, it's straight back, right? It doesn't go underneath, right? So, water waves at the walls are open ends. See? It's your real life experience that helps you understand this. Okay. You take the wave, you push, then got a crest will go to the wall, right? The crest will come back. This is because when you are young, you have to turn the wall will have to turn back. You right?
Yes.
Remember, is this something that is in your experience? No. Never seen before. I don't know, my right? See how? Go swimming pool never go swimming pool I use the water bottle can simulate when you try to splash the water around, you see that when it hits the wall, right, it doesn't go underneath. Yeah, the crest doesn't become trough. So actually the wall end, right, for water waves, right, is considered open end. Right, you see the crest bounces back and forth. Yeah, drink it further. Right, got it? Right, make sense? Agree? Agree? What? But it's I think you can drink the water. Brandon, you agree? So water waves at the end is open end. If it's open end, is it node or anti-node at the wall?
It should be wait, the one that goes hard.
Open end. So it's anti-node. Okay, so that's your hint. If you didn't get C, the wall is anti-node. They want the distance between anti-node to node. But Abi just now show us that node to node is wavelength over 2, right? So distance of anti-node to node is half of that. So it's wavelength over 4. So the wall is an anti-node. This is because it is a free end. So if they want the distance between the anti-node, the first node that will appear, the first node is a quarter wavelength difference. So you're going to try to sketch the graph and figure out where 1/4 distance is. Okay. So my wall is here. So I want to identify the same cut on the wave. So this is one wavelength. Right, this is 1/2 wavelength. This is 1/4 wavelength. So it should be some point that is below the equilibrium, but not at the maximum or minimum point. Okay, and definitely not past the So is it reasonable that it's C? Right? This is empty node. This is where my node is, and this distance is wavelength over 4. Right? So which of the points fulfill your criteria? Yeah, it's C, right? Because D is actually too near D is the equilibrium point. It's not the equilibrium point. It's too near the wall already. Right? And it's not anything further. It's definitely not A because the anti-node node distance is lambda over 4. So it can't be more than 1 wavelength away. Right? So the first node is here. Right? After the anti-node. So if you manage to form standing wave with water waves on the wall, right, you will get anti-node at the wall. So it will be anti-node node, anti-node node. You will just reflect. Okay, so yeah, okay, good question. The question is, what is the reflected wave look like, right? So my wave continues past the wall this way, right? So the reflected wave will just reflect back along the wall the same way. So it will go up. I don't know how to sketch this. How it look like. Yeah. So the reflected wave will be this thing to the other side.
And if it's a 180 flip,
then there's no 180 flip because it's a free end.
so it's fixed edges.
Fixed end, then you'll fit. So water waves hitting the wall is not fixed end. It's free end. You know it's free because actually you know the water at the edge of the wall, right? It's actually free to move up and down in the first place. So it's actually free to oscillate. Right?
So how do you, there could be different kinds of waves, so how do you look at the
Yeah, so actually, you're right. Actually, we need an exhaustive understanding of all the different kinds of waves and when they hit surfaces. So the hardest to visualize is the electromagnetic they interact with the wall very differently. Right? But for the mechanical waves, it's very easy, right? Like the rope, you already hold the end, right? There's no way it could oscillate. So if I force a standing wave with it, it must be node. But if the whole end is free to move up and down along a pole, like with a ring and a pole, then obviously that one is free to move, it will be anti-node. So it's just whether the end is free to move or not. That will determine whether there's phase change. Right? So for water wave, most of the time you all wouldn't know. But then now you think back about it, actually when you push water to the wall, it always comes back on top, it doesn't flip itself. So you know that it's considered free end. And it's free end because the water particle at the end is free to oscillate up and down.
Why is it free?
The what?
Why is it free end?
Because the water particle at the edge of the wall is free to move up and down. The water doesn't have that much intermolecular forces in the wall that the particle is stuck at the wall. Right? Yeah, so the water particle at the wall can really move up and down. Okay. Okay, so this was actually quite a difficult question if you ask me, because hard to justify whether the water is an anti-node at the wall or not. Right? Would you have thought that it was a node at the wall? Because the wall seems to be a hard end, right? So it's not about hard or soft, it's about whether it's free or not free. Okay, question 4 is very fun and very interesting. So let's take a look. Madam, show us the working.
I don't know if I'm correct. Sorry.
Yeah? See though. The mic will pick up. So let me see. Yeah? This is not right. Is that? Okay guys, Amanda, oh boy, go. One time to the bottom. That. Okay, so Amanda got C. Okay, you want to explain to the class how you got it? Another one?
Okay, so basically, the question states that RST all have zero density, which means that they are all nodes. So, you all know that the distance between nodes is half a wavelength. So, to calculate a wavelength, you basically just do times 1.5, because 1.5 is the distance between nodes. Then after that, you calculate using V equals to F lambda, you will get your frequency.
Good.
So, that's it. C.
Okay, good, thanks. So, you know, some of the reason why you might have mistaken that R and S and T are not nodes is the word intensity. Okay, you know, when I showed you the video of the standing wave, right? I showed you a video of standing wave, remember? The two waves moving to one another. Even the anti-node oscillates, right? So there are actually a period of time where the whole wave is horizontal. Now, when I measure intensity, right, let's say I use some microphone or speaker, right, it doesn't detect the fluctuations of the anti-nodes. It just detects it as loud. Okay, that means it doesn't care that the displacement is changing. Okay? So for example, right, when this light wave is coming to my eye, the light have created some kind of standing wave pattern. So by right, there's node, antinode, right? The node part will always be dark to me. So it's zero intensity portion. But the antinode, although it's oscillating, right? My eye won't see it as oscillating. My eye will just see it as it's bright. Okay, don't worry, we talked about the diffraction pattern, right? It's the same thing also. The bright spots actually have oscillation in electric field. But our eyes don't see the oscillations. I just see that, okay, the average of over time is that there is light energy there. So intensity is about measuring energy. And energy is proportional to amplitude of oscillation, not displacement of oscillation. Right? Remember in SHM, our formula for energy is half m omega squared a squared or something like that, right? So it's actually dependent on the amplitude. It doesn't depend on instantaneous value of the displacement. Okay? So same is true for my nodes and antinodes. Zero intensity means over a period of time, here got nothing on. Nothing means no oscillate at all, means it's the node. So in between is actually maximum intensity. This part will be max intensity. Okay, so that's why R, S, and T are the nodes. Okay, so whenever we see zero intensity regions for standing wave or for diffraction pattern, we're talking about nodes of disruptive interference. Okay, and this is a microwave transmitter. So actually this has a bit of bearing on the kind of things you all do at home. You all got microwave cold food before?
Microwave what?
Cold food.
Yes. No.
Never ever microwave cold food before to turn it warm.
No.
Is it because your family believe that microwave is dangerous?
Family delicious all the food.
Huh? Fair enough. Okay, so those of you who have microwave cold food before, right? Have you ever noticed that after microwaving, some parts are cold, some parts are hot?
Yes.
Why?
Always a bit hot.
We haven't reached all the
Always the inside is then cool.
But it's electromagnetic wave, it goes through the whole thing. And it's not outside hot, inside cold, right? It's not, right?
No, it is.
It's not, it is not. Inside got hot and cold parts too.
What?
Yeah, the inside got hot and cold parts.
That's awesome. Actually.
And sometimes got outside parts that are cold too. Then you eat inside part is hot. No, it's not between the, but with progressive wave, then the wave pattern should go through. It is not. Your microwave oven forms this pattern. Your microwave oven is designed to form microwave standing waves inside itself. Some parts have nodes. So those parts don't get heated up. Some parts form antinodes. So they get heated up. And that's what your plate is for. Your plate is to try to turn the object around, right? So that it gets node and antinodes at different times.
Doesn't mean the center is still.
I mean, it doesn't necessarily mean the center is an antinode. It could be the center is an antinode.
Oh, so is that what the thing is for?
Yeah. So that you can try to retrieve the points of the foot between the nodes and antinodes.
Oh, that's so interesting.
It is, right? Okay, now, how do you measure this? Which means to say, right, that actually you can get the node distance on your foot, right? If you know the wavelength of a microwave used in a microwave oven. Right? Can you think of an experiment in which you can do this? Okay, if I give you some hints. First, you cannot let the thing rotate. So what must you do?
Remove the plate.
Yes, remove the plate. That's the first step. Okay, because the plate is specially designed that it will fit the groove in the middle that has a motor turning the plate. Right? If you put a normal plate in, it won't rotate.
Oh, like maybe some material that's connected to.
Okay, no, it won't rotate because the plate must fit the groove, then the thing will turn the plate. Okay, the plate, if you put a normal plate in, it won't turn. Okay, that's step one. Step two, you need a flat type of material. What food do we eat that is commonly flat?
Bread.
Yes, okay, bread. But bread, right, hard to observe which part is hot, which part is cold. So what kind of material you can put on top of a bread, right, that when it heats, it changes itself?
Cheese.
Yes! So, you need a plate, you need bread, and you put a layer of cheese on top. There must be the square cheese. And then, right, you microwave, right, after a while, right, you will see, right, that this cheese, right, will have some parts melted on.
The wavelength was so big.
Yeah. centimeters.
Oh, I thought it was so much smaller than that.
Yeah, it's microwave got micrometers all the way to several millimeters lah. It's a big range.
Oh.
Yeah. So actually, right, you will be able to get a standing wave pattern. If you want to more accurately display this, right, you go YouTube and watch. Put LED into microwave oven.
LED.
Yeah, you put an LED array into microwave oven, right? You see some of the LEDs light up and some of the LEDs not light up. The LEDs that light up are at the antinodes, closer to the antinodes. Then the LEDs that don't light up will be at the nodes. Because in the end, the electromagnetic waves is producing an electric field, and the electric field drives electrons in a circuit, just like what we talked about in the current lecture. Yeah, so it causes the electron to move a little bit inside the LED, then it will light up.
So then why don't they make like microwave, right, like the thing closer to each other? Do they like way of cooking, like see the problem?
Maybe it's not convenient to produce that wavelength long. Okay, then the second thing you notice is that liquids, right, actually generally don't have the hot cold portions, right? Yeah, because in liquids you have a lot of convection current can distribute the heat more efficiently. Whereas in solids, especially something like there's a lot of very little conduction points. Right? That means the material is quite sparse one. Then you notice that there's more hot cold points because it takes, and the longer you microwave it, the more even you'll get because you're giving it time to conduct heat. Also, it's true, right? That means you take an egg, right? You put in the microwave, it will explode, right? Because the heat is able to go through the surface. Because the heat is not produced by heating the top. That's why your microwave doesn't heat food from the top. That's why microwave is such a good heating apparatus, because it can heat food even on the inside. Right? So your egg will be cooked inside, but if you are vaporizing things inside, then it will turn to gas, and then your egg will build up pressure, and then your egg will explode in the microwave.
Of course, there's some.
No, because the egg is like a shell, it doesn't let the air out. Then the air expands, and boom. So in my uni days, right, we were then free, right? We keep watching this YouTube channel called Can You Microwave That? Then they put a lot of funny things in the microwave, and some of the things end up making the microwave itself explode because yeah, it's not supposed to microwave those stuff. So you can go watch those.
I thought you put a spoon inside, right?
It was stuck lah. Yeah, because metal react differently. Metals will reflect the wave. So here we're talking about non-metal surfaces. The waves will just pass through them. Okay, now we know that it's standing wave that's causing this already, right? The next thing is what's the mechanism for producing the heating effect? Okay, you're chem students, so you should know this.
Or the water.
Okay, what's water molecule, right?
The line of the wave, right?
What will align?
The position.
Yeah.
Oh, actually.
What part of dipole will you So this part is more delta minus. See, I haven't talked about my chem thing.
It's one delta minus.
Yeah, so this part delta minus, this part delta plus, right? Because oxygen is more electronegative, the electrons from the molecular bonds spend more time around oxygen. So this part tends to be more negative, this part tends to be more positive. Right? So this is a dipole. It's called a dipole. In physics, when we have a dipole, right, and you apply the electric field, right, basically you have the equivalent of this. A dumbbell bar, one side plus, one side minus. So this thing will try to spin around. Then you suddenly flip the electric field, right? And it's like, whoa, and then you flip this side. If you want to calculate the microwave frequency, this thing is happening 10 to the power of 10 times per second. So can you imagine what's happening to your water molecules? Like, whoa! Right? And actually this will cause them to knock around all the other particles, and that's why there's heat transfer. It's basically simple agitation. Right? Basically the water molecules are being knocked around, and then they knock everybody else, and everybody else gets hot this way. Because kinetic energy is the measure of temperature, right? This relates to our temperature module. Right? So basically that's how your microwave works. But it's quite complicated. Then you try to explain to the primary school kid, right? You're like, I don't understand any of this because he doesn't have an understanding of waves, he doesn't have an understanding of standing waves, he doesn't have an understanding of electric dipole, and then of course he doesn't understand that temperature is related to kinetic energy of particles. Right? So the same thing is true. If you try to heat up food with no water, it won't heat up very well. It will rely on the atmospheric water molecules to do the heating, which means the density is far lower. Right? So this knocking effect is far less. Right? Conversely, if you take something with molten ions, but the ions have size on a dipole, right? Then this effect will still be there. Yeah, okay. That's one thing. Okay, now you need to correct me for another thing. Okay, so this is the correct explanation, right? Of how microwaves work. There's a wrong explanation. So some students and some teachers even, and some secondary school teachers might have told you that microwave works this way. it's wrong. Okay? Now, there's a bond here. We learned in thermal physics, right, that when you have bonds, right, they can be in excited states. So the bonds will oscillate. Right, they will they do this or this. There are two modes of oscillation, right? Okay? By right, if the wave frequency matches this frequency, right, it will have resonance effect. Yes, that's true. There will be this resonance effect. That's not how microwaves work in a microwave oven. Why? I mean, it's a possible heating mechanism, but this is not how resonance works.
Bro, I thought resonance is the sharing of a thing.
No, resonance is when you have a driving frequency equal to the natural frequency. Remember definitions?
Oh, that was it.
Yeah, that's the definition of resonance, right?
Definition.
Yeah. You get driving frequency equals to natural frequency, then you get maximum amplitude of oscillation. So that's resonance. Why is this not resonance? Yeah, because the driving frequency is not the natural frequency. This natural frequency is actually different from the microwave frequencies that we use in a microwave oven. If you look at a microwave oven, the description of radiation used, right, it can use a large range of frequencies. But this means it must be very specific, which means you must only produce microwave of one specific frequency, then you can do this. And that's not how microwaves are made. They don't have the element that produces this particular frequency. Okay, not bad. I want to see the tutorial question can talk about cheese and microwave and electric dipoles. So see your chem knowledge useful. Tell me still that you all applied electric dipoles to physics question.
So you apply to read.
No, but ask you all say one now. I'll just
Bro, it's kind of silly. Let's say bread, cheese, and dipole.
let's go indigo again, Okay. Oh good. So question 4 is the end of easy questions. Question 5 starts to be more difficult. Yeah.
Why must we use the specific way? Why do you use
Yeah, then you know the transfer of energy won't be efficient because the amplitude of oscillation is not large. So actually, although I said that this is not resonance effect, right? Creating standing wave is also some kind of wave called resonance effect. Okay, so there is the same reason why in your musical instruments, why can't you just blow any musical instrument and try to make sound with it? Why must the tube be created a certain way? Why must your guitar have a certain size in its box? Just take strings and you play. Like you just take two things and then you just try to make the string move. No. Cushion have its own resonance box below also, right? Right? Huh? I think so.
That's a question not right.
And also, when you do a Guzheng string, they got particular length one. It's not any length also can one. Right? And the same thing is true of all your wind. Who's in band? Right? Band got wind instrument. Yeah, you know the wind instrument, they got pipe lengths one. So all of these musical instruments need resonance so that the amplitude of the sound produced become very, very loud. Right? Whereas if you try to take strings and plug, right, you think this person standing there can hear the string being plugged. Cannot hear one. So this resonance effect makes you think for the sound loud and actually gives you your different sound octaves, right? Different notes. Okay, so anyway, we're going to look at this experiment, which is something similar. So in question 5, we got 0.68 meters cubed, and then you're going to produce sound waves with it producing standing waves. So the standing wave is produced here. Okay. The air particles here, are they at open end or fixed end? Yeah, it's open, right? Because the air particles are free to move up and down. Okay, so if it's open end, then what point is this? This one must be ND naught. This one must be ND naught. Okay, so these two must be ND naught. So which means all the different modes of standing waves you can get in must produce ND naught for the two ends. See how you the board already? Today? Well, let's get the three standing waves. You just need to draw a standing wave with the ND notes at the two ends. Let's try. Come.
That's mine.
So you draw the line on top and below, and then you try to catch the standing wave. Huh? Yeah, I'll show you that first example. First example will look like that. Here ND note, right? So this is the simplest one you can draw. So you draw like that, and then this is the one. next one.
Very, very
Very tight.
Hi. Yeah.
Hint, it will look like sweet wrapper. The two ends are to be open. You try to complete this, I think you get another two. Try to extend it. I think okay, that's an open end.
You say
It's
yeah.
open already.
Oh, this is the graph.
Okay.
Why is there a graph?
Okay, good. Right. So you can see these two are open ends, right? So this is the next one. One solid line, one dotted line.
How is it this, bro?
What's your daughter?
That's solid.
There's no graph.
Yeah, it's not graph, it's the.
They say graph what? You should line
The shape.
So what was that daughter like?
The dotted line is half what happens half a cycle later.
So they want to draw the two lines. They ask me to draw graph. Then like,
Yeah, this is the graph.
sorry, you put up. Right, that's right.
Okay, also it was you. This is the same as you. Then oh, you want to draw the next mode. The next mode means you want to have shorter wavelength. So you're going to fit this whole shape inside. Can you get it? Okay, start here again. Okay. Go all the way to the bottom. Yeah, okay. Then the dotted line. No, I'm going to be negative to zero gradient. Yeah.
Where do you use
Okay, good. Now one more.
Oh, example.
Yeah. Okay, stop already. See, just so you can end here, right? Now you can end here one. Okay, yeah. Not the dotted line. Okay, good. Okay, now, right, how many wavelengths? Hey guys, are you all watching Teaching How To? So you got the first three modes already, check your own work is correct, huh? Just check your work. Okay, how many wavelengths is this? This is peak, this is trough. So how many wavelengths is it? Okay, right. Just right here on the right side, L equals wavelength over 2. Okay, next one. Next one, how many wavelengths? Yes. Then right, L equals lambda. This one? L equals? Yeah, I agree with you. Okay, now, I tell you that the sound waves all have the same velocity v. Calculate the frequency for each one. Okay, you can write v equals to f lambda. F equals to v over lambda.
That's not high enough.
Equals to in terms of L.
Yeah, whipped cream is one of these.
You got lambda over the camera. Okay, good. Next time. Okay. So how's that confident? You can do it, man. Okay. Alright, so good job. See how I have managed to complete it. Although it's not but Abby. Right. So, how was your criteria for drawing the graphs? You have a criteria, right? The n cannot be anything, right? The n must be a particular thing, right? What is it? Yeah, the n must be ND node. So let's check. This is the simplest graph that Sui Hao can draw. He can't draw half of it because this is the n and the ND node. Right? Because this is the node. So you can't just draw this half. You need to draw until here. Right? Now the next level you can draw, right? I like to call this one street wrapper. Because it looks like street wrapper, right?
Wait, when they ask, is it you draw the second one in dotted line?
Yes.
I thought both must be solid.
No, second one dotted line can.
But if it's not solid, is it wrong?
I think dotted line makes more sense because dotted line represents half a cycle later.
Okay. So it's because the node is no resonance, that's what I'm saying to you.
Huh? No. These are called resonant modes. Modes, M-O-D-E. The mode.
Okay.
Right? They're all called resonant modes. As long as we have formed the standing wave, we are called a resonant mode.
The top must have like some gap, right?
I mean at the end, right? It's not exactly at the end. It's called something called an end correction, but that's not very important for now. We just observe that this is the shape. So the pattern form is if you're having an open tube, it must be ND node both sides. So this is the simplest one you can get. The next one and so on and so forth. Okay, now the sound wave coming through, right, all have the same speed, the speed of sound. Agree? So this means to say that although the tube length is fixed, the wavelength is not fixed because you can see that you can only fit half a wave here. This one you are fitting one entire wavelength because peak to peak, right? Then this one you are fitting 1.5 wave because it's peak to trough, right? So each L is equal to a different wavelength, right? So we'll call this lambda 1, lambda 2, lambda 3. Then since the speed are all the same because it's still the same sound wave going through, and they all have the same speed, we get different frequencies. Frequency 1, frequency 2, frequency 3. So basically, the frequencies are different in each tube. And this actually corresponds to your musical instruments that are this kind of. Basically, when you use a different hole in your wind instrument, you're shortening the tube or lengthening the tube. You're getting a different frequency of sound. In this case, all have the same length, but because you're getting different modes inside, you are actually getting different frequency as well, so you get a different sound. Higher frequency, the sound will sound sharper, high pitch. And lower frequency, low pitch. So actually this is the science of music. It's the entire field of study itself, science of music.
Oh, that's cool.
Yeah, it's pretty cool. Let me just tidy up to see how it's working. So this is V over 2L. This is V over L. Yeah, right meter. Then this one is 3V over 2L. So actually you will see a pattern, right? The pattern is for the wavelength
Increase by half.
yes, so the formula for increase by half is
Oh,
Just a formula.
yeah, it's not a memorized formula. It is I'm creating a mathematical formula from my understanding of progressions.
Divided by n times.
No, it's not divided. It is 2n plus 1, 2n minus 1 L. Because this one is wavelength is 2L, right? So it's 2
n minus 1 times L over 2 is half.
4 minus 1 is 3. Wrong, huh?
Wait, so why you use formula though?
Shouldn't
Why
it
not over 2? Half
shouldn't
is
it be n? N minus 2.
Okay, so it's n. This one is 1. This is 2. This is 3. But if I bring this over, it will be 2L. Lambda equal to 2L. So it's like 1, right?
Wait, so the 2n minus 1 is for the whole source of the
I mean, it doesn't matter. I know that I see a pattern, right? I can always write a progression for it. Right? Okay, never mind. We write for the frequency. Frequency is easy. I calculated, right? This one I haven't calculated, right? So for the frequency, right? It is V over 2L, then V over L, then 3V over 2L. So the coefficient is I will end up with half. I must end up with half for 1. So it's
This is a math class. Why you
2n plus 1 over 2. So it's n plus half. No, it's n minus half. 1 minus half is half V over L. Then if I'm F2, n equal to 2, 2 minus half is 1.5. Wrong. Sorry, my math sucks. But you get what I'm trying to do, right? You can get a progression for this one, a GP. Or is it an AP? GP, right? Either help me out here. What's the formula?
Just half n.
So what? F is half n.
Yeah.
Okay lah. But this is n equals to 3, then I can, okay, can. Okay, sorry. Yeah, okay, I know how to see. This is 2v over 2l. So it's 1v over 2l, 2v over 2l, 3v. Okay, so it's n v over 2l. Okay, can. Sorry, don't judge me, okay? Math was my worst subject.
For real?
I like physics.
I like the idea of physics. Math is just like, whatever can do.
So what's your subject?
Same as yours. Yeah.
It's only going to be.
Okay.
What is it?
I'm actually more of a language person actually.
Huh?
Yeah.
So
So guys, don't just shoebox yourself
you
into
just
one
got
subject.
an A lah.
You study that.
More of a
What?
language. It's like an
At A level? No, I didn't. I took LAJ, Japanese in uni, level 1 only. That's basic stuff, but not enough anime but no.
So you can speak.
No, I can't. I can understand a little bit, like
Bro,
Asian
you
words.
say until like he damn good at speaking Japanese, bro.
Oh, no.
No, him. No, bro.
Okay, all good. So these are the notes, right? Let's see what else the question wants. The question says, sketch graph to show the profile of the wave. So this is basically what they're asking for, the profile. Now, just before we end class, let's just quick check. This graph, right, what does the y-axis represent?
Amplitude.
No.
Of
So there's negative amplitude. And
Yes,
it has
okay.
not the axis yet.
n, but there's no axis here, this is the pi only.
Then got y, there's no x.
Okay, the x is here lah. This is the x.
Wait, so that's the graph that you have to draw, is it?
Huh?
That's the graph you have to draw, is it?
This is a graph. This is a graph.
It's not a vertical. There's no vertical one.
Yes, okay. Remember, what kind of wave is going into the pipe? Some wave got up and down one, man.
So it's displacement. Is it?
Correct. So the y-axis, right, is actually represent that particular particle there, was it moving left or right? Okay.
Displacement processor.
Basically, the misunderstanding most students have when they draw this graph, they know how to draw this graph. See how you know how to draw it? Can, right? Okay, you know how to draw this graph, but they think, right, that the air particles going up and down like transverse wave. It is not. Air particles go forward, backward in some ways. So the up, and this is actually a graph. That up is basically represents the particle here has moved to the right, and negative means particle has moved to the left. So this is the y-axis represents the left-right displacement of the particle.
So displacement aspects. Displacement.
Yeah, this is a displacement distance graph. Lor. These are displacement distance graphs in your pipe. So basically, what I'm trying to say is, you can actually find the right fraction compression points after that. Okay, so now we're done with this A. Okay, we are supposed to label the nodes and antinodes respectively. So it is, Ethan, you help me? Yeah, it's node antinodes. Okay, then? Okay, so this is the labeling of the nodes and antinodes. Okay, we're done with that. With reference to your graph, determine the wavelengths and frequencies. So the wavelengths, now we need to make the wavelength the subject. So lambda 1 equals to 2L, lambda 2 equals to L, and lambda 3 equals to 2L over 3. Am I right? Yeah, 2L over 3. Then frequency, because the wave velocity is constant, we use V equals to F lambda. So how did that for us? Then we got all the different frequencies. Okay, of the standing wave. Now we're done. Okay, so we left with one part. Part C. Let's quickly finish this and we call it a day. Alright, this last part says, as the frequency of sound is increased, identify the two lowest frequency if I put a microphone at 0.17 distance away from the edge here. And that's 0.68. So first, I got to get 0.17 as a fraction of the total wavelength. You don't know how to do this part, huh? This is the hardest part of the question.
So what's the answer?
500 and 1500.
Oh shit, I didn't get 300. I got 500 and 1000. Yeah, I
So,
also
so this means some method was wrong, right? Okay, let's see. What is the ratio of these 4:1, right?
Yes.
So the distance of the microphone equals to 1/4 of L. Now, they want to find where is a node. Agree? If they want to find where is a node, right? This means, right, this must be where nodes are. And this node, and this is a node, this is an empty node. Agree? Which means, right, this must be dm, the microphone, is actually the distance between the node to one of the empty nodes. At the lowest level, there is no more nodes in between. Right? So this is the node to empty node distance. So this one must be either wavelength over 4, because node to node distance, earlier on remember node to node distance is wavelength over 2, right? So node to empty node distance is wavelength over 4. Or the node to the next empty node distance is
4 plus.
plus what?
Plus 2, right?
No.
Plus.
So the next one is actually node, empty node, node, and node, empty node, node, empty node. Yes, 3 lambda over 4, because you have to have two more node empty node distance in between. Then the next one will be good. Now that we know that this is what this distance is, we know it's multiple of L, right? So we are able to go and substitute now. This distance is 1/4 L. So 1/4 L equals to wavelength over 4, 3 wavelength over 4, 5 wavelength over 4. So L equals to wavelength, 3 wavelength, 5 wavelength. Okay. So now we can make wavelength the subject. Wavelength 1 is L, wavelength 2 is L over 3, wavelength 3 is L over 5.
Wait, how is lambda?
Because these are the three, okay, this one is 0 nodes between the microphone. Then now the next possible time is that actually one more node in between. Then the next time is that 2 more nodes in between. Basically, that's checking how many nodes I can fit inside. So of course, this could be infinite. I could have like lots and lots of nodes in between the microphone. So they're checking which is the lowest field. Right? So this is the lowest, next lowest, next lowest.
Oh, okay.
So this corresponds to 0 nodes, 1 node, 2 nodes in between the microphone. Right? Okay, so once we get this right, lambda, right, we can get F. F equals to V over lambda. So this is going to be V over lambda 1, that's F1. F2 is going to be V over lambda 2. And F3 is going to be V over lambda 3. Okay, and then you can calculate this out. This is 340, then this wavelength 1 is just L. You will get the first one to be 500 Hz. The second one to be 1005 Hz. The next one will be 2005 Hz. I think so. Not 2000. Sorry. Not 2005.
Also on the 5.
Yeah, 2005. Yeah. So I haven't calculated these values out. So I'm supposed to calculate these values out. So that's 250 Hz. This one is 500 Hz. And this one is 750 Hz. And the reason why we can calculate it is because they have given us the velocity and the length. This one, the wavelength is 1.36 meters. This one is 0.68 meters. Another is 0.454 meters. Okay, so just take note of this stuff. Maybe I can just send it to the class chat and then you all can go over it. Sorry to pull you all back. What lesson is next?
Break.
Okay, sorry, go over break. I know this last part quite heavy. We can